Okay, so hello everyone. Maybe it's time to start this first webinar of the Combinatorics seminar of Rényi Institute. I will talk about some saturation problems, and this is joint work with Balázs Keszeg, Nathan Lemons, Ryan Martin, and Demeter Pálvölgyi. So, okay. So a little bit about saturation problems. So in my view, they are little brothers of extremal problems. So in extremal problems, we are looking for largest combinatorial objects having some kind of properties, some prescribed properties, as opposed to saturation problems when we are looking for minimum sized graphs, hypergraphs, or set families with some prescribed property. Okay, so let's see some examples. The property of being a triangle-free graph. We know from the famous theorem of Montel that if we have an n-vertex triangle-free graph, then it can have not more than n squared over 4 edges. This is sharp as shown by the balanced bipartite graph. And so this is the extremal problem. And the corresponding saturation problem asks for the minimum number of edges that an n-vertex graph should have, such that the graph itself doesn't contain a triangle, but no matter how we add any edge that is not there, then this new edge will indeed give us a triangle. And this number is n minus 1. This is shown by, for example, by the star. If we add, so it's k1 n minus 1, if you want to have it in a formal way. So the complete bipartite graph with part size 1 and n minus 1. And this is minimum possible because if you have less edges in a graph on n vertices, then it's not going to be connected. So if you add an edge that joins two different components, then definitely no cycles. So in particular, no triangle will be created. Okay. For graphs in general, so not only for triangle-free graphs, but if we forbid a graph f, and the extremal problem is that what's the most number of edges that we can have without creating a copy of f, then this is settled more or less, at least for non-bipartite graphs, by the Erdős-Stone-Szymanowicz theorem. The answer is quadratic. And we also know that this extremal number is linear if and only if the graph, the forbidden graph f, is a forest. And the corresponding saturation problem is that now we forbid the graphs, well, in my slides, it is now denoted by G. So what we want is the minimum number of edges in a graph with n vertices such that it doesn't contain G, but any addition of a new edge would create a copy of G. And Cassoni and Tuza in 1986 showed that no matter what the graph G is, it is always possible to create such a saturating graph, G saturating graph, with a linear number of edges. What about hypergraphs or k-graphs, k-uniform hypergraphs? Well, in this case, the Turan problem is very much unsolved, so we don't know too much about the extremal problem, and we don't know the exact values for most of the for the saturation problem, but we have a result by Pikurko, which is an extension of the Cassoni-Tuza result. So observe that if we are talking about k-graphs, so k-uniform hypergraphs, then the total number of possible hyperedges is, of course, n choose k. So the order of magnitude is n to the k. And Pikurko's result says that no matter what the forbidden hypergraph H is, one can always create a hypergraph on n vertices with big O n to the k minus 1 many hyperedges, such that this hypergraph doesn't contain H, but adding any new hyperedge would create a copy of H. Okay, so let's get closer to our topic today, forbidden subposet problems. So Sperner's theorem is one of the theorems, one of the two theorems that are always on my slides. The other one is Erdős-Korodó. Today it's Sperner because I'm talking about containment results. So what does it say? The theorem of Sperner from 1928. It says that if we try to gather as many sets as possible, I mean, as many subsets of an n-element ground set as possible without having to one containing the other, then the best one can do is, or what can get, is n choose n half, and this is sharp shown by the family when we gather all the subsets of size n half. And this result was extended by or generalized by Erdős. So this time we do allow some pairs in containment. What we do not allow is a nested sequence of k+1 sets, also called a k+1 chain or a chain of length k+1. So in this case, Erdős determined the maximum number of sets that we can put to a family without having these this forbidden configuration. And similarly to Sperner's result, what one should do to obtain the best family is to take sets of only k possible set sizes, and the set size, to maximize this, one has to take the set sizes around the middle, so around n half. So the extremal number is going to be the sum of the k largest binomial coefficients. Okay, and then so there are lots of applications to both of these theorems, and there are lots of generalizations. And one generalization is due to Jussi Katona and Tamás Tarján from the early 1980s. And the way how they viewed these two results, that there are some forbidden containment patterns here. Sperner's theorem that forbids any kind of containment, and Erdős's theorem forbids the containment pattern of a chain of length k+1. So how one can generalize this? So these forbidden containment patterns are described by posets in the following way. So here on the left-hand side of this picture, you see the V poset consisting of 3 elements, one at the bottom and 2 larger than that, and the blue element and the green element, they are incomparable. And so how this poset can be realized by sets? Well, here are 2 examples, actually. One example, probably the more natural one, is that for the red one, we have a very small set, and this is contained in both the blue set and the green set. Well, this is done also here. The difference between the 2 pictures here, that here we have the extra containment, that the blue one is also contained in the green one. Well, it's a matter of taste whether you consider this as a problem or not. But whatever we have here is that whenever there is a containment, I mean, there is a relation in the poset, there should be a containment among the appropriate sets. And the difference between these 2 pictures, or these 2 configurations of sets, is that here we only have containment exactly when there is relation in the poset, and here there are some additional ones. And so therefore we distinguish between 2 notions. This is something that is called an induced copy of this poset with sets, and this is a non-induced copy of these posets. And here are the formal definitions. Okay, so now we can say that a family of sets is P-free if it doesn't contain a non-induced copy of P, and it's induced P-free if it doesn't contain any induced copy of P. Okay, and so the extremal problem is to determine the maximum size of a P-free family or of an induced P-free family in a ground set of size n. And this is denoted in the non-induced case by LA and P, LA for largest, and with a star for the induced case. So it will be the same for the saturation problems. Whenever you see a star, that is for the induced problem, and whenever there is no star in the formula, then It is for the non-induced problem. Okay, so with this notation, Erdős's theorem just says, sorry, that, well, of course, then for chains, there is no difference between induced and non-induced because all elements of the chain are related. So therefore, all sets should be in containment. So the LA function and the LA star function are the same. And according to Erdős's theorem, so C sub k plus 1 is the chain of, of length k plus 1. Then, and this is the extremum number. Okay. A couple of words about what do we know for the extremum problem, and then we move on to the saturation problem. So because any poset on k elements is a non-induced subposet of a chain of length k, so therefore Erdős's result implies this bound for any poset p. So because we know that for an anti-chain or for any poset that contains at least two comparable elements, an anti-chain is a family that doesn't contain that particular poset. So for any p, we can have a p-free family of size n choose n half. So therefore, it immediately gives the correct order of magnitude of this LA function, of the extremal function. But this is not an immediate consequence of Erdős's result or of any other result for the star, for the induced version. So this was just recently proved by Abhishek Metuku and Dimitar Pavlogyi that the same order of magnitude is true. So the induced extremal function is also in the order of magnitude of n choose n half, no matter what the forbidden poset p is. Of course, the constant depends on p. Okay, so we know the order of magnitude, but we don't know in general whether the limit exists. So it's an open problem, both in the induced and the non-induced case. Okay, conjecture. So for lots of the for many posets or for many classes of posets, the extremal function is known either precisely or asymptotically, but it is a wide open problem for in general. But there is a conjecture that is believed widely or in general among people who deal with these kind of problems. And the conjecture is that actually to get the optimum, get a maximum size or an asymptotically maximum sized family, one has to take whatever Erdős did for chains. So what did Erdős do? A reminder, he took to avoid chains of length k plus 1, he took only sets from k levels, sets out of k possible size, and to maximize the number of sets that we can get via this construction, we had to take middle levels. And now the general construction is that take as many middle levels as you can without creating a non-induced copy or an induced copy, but depending on whether you are in the induced or non-induced case. And whatever you get there is going to be the asymptotically optimal. Okay, so this is what the conjecture says. Okay. So that's it, what we have, or what I wanted to say about the extremal problem. And now let's look at the saturation version, the real topic of today's talk. So we will be interested in these two functions, the set and the set star function. So the non-induced saturation and the induced saturation function. So what we are looking for is the minimum size of a p-free family. For this time, I'm talking about the non-induced case. So the minimum size of a p-free family is such that whenever I add a set that doesn't belong to this family, then after adding this new set, there will be a copy of P created, a non-induced copy of P created. And if I change non-induced to induced, then I get the induced saturation function. Okay, so let's recap the history of this problem. What do we know already about this problem? So it started about 10 years ago when with Donny Gerdner, Balázs Keszeg, Lemons, Corey Palmer, and Demeter Pavölgyi, we observed that, well, the simplest posets are, of course, chains, totally ordered set. So we observed that if we consider the chain of length k, then here's a construction, take, and it works for any n. So take small sets in the sense that take the first k minus 3 elements of your ground set and take all the subsets of this part of the ground set and take their complement. Well, here we have 2 to the k minus 3 elements and their complements. So altogether, that's 2 to the k minus 2. And our claim was, or what we observed, that this family, I will show you in a minute, that this family is actually CK saturating, which means that there is a bound on the saturation number. And again, because we are talking about chains, so therefore the non-induced and the induced saturation number for this particular poset, there is no difference between the two. But in any case, so what we observed via this construction is that there is a constant bound that doesn't depend on the size of the underlying set. So why is it a good construction? Well, I need to show you two things. First of all, that this construction doesn't contain a chain of length k. Well, how this family looks like? Well, I have this small part here, the first k minus 3 elements, and all its subsets. And I have their complements. So their complements, they all contain whatever I have here in this large interval. So all the elements from k minus 2 to n. And of course, whatever I want to have here, I can have that because I just take the complement with respect to here, and then by definition, my set is there. So basically, this construction is just the Boolean lattice on k minus 2 elements because this part behaves just as one big element, if you wish. So this construction is poset isomorphic to 2 to the k minus 2. So therefore, it contains only chains of length k minus 1. So that's why we don't have a copy of a k chain in this construction. So this is half of the thing. Now I have to show that, okay, it doesn't contain chains of length k, but if I add any new set, then it will contain a k chain. So why is that so? So let's add this green set H, and let's partition H into two parts. The part here in the first part, among the first k minus 3 elements, and the rest. So what do we know about these two parts? Well, I don't know anything about the first part, but what I do know about the second part is that it's neither empty and nor the whole interval here. Why is that so? Because if it was empty or if it was the whole interval, then it would be actually in the family because all those sets are in F. So because this is a newly added set, so it's neither empty nor the whole interval. Okay. Now what I do is, okay, let's consider now the first part of this green set, H1. And in here, among the blue sets, let's create a maximal chain until H1. Then I insert my green set. I add the appropriate red element, or red set, meaning that I now take here all the elements. This is part of my family, so I can do that. And from then on, I just take a maximal chain until the whole underlying set. And if you count, that is going to be a chain of length k. So this is how I show that, or how one can show that the addition of any new set would create a k chain in this construction. Okay, so this shows that for the k chain, the saturation number, actually it's independent of n, or there is a bound that doesn't, an upper bound that doesn't depend on n. So how sharp is it, this construction? Well, as long as k is not more than 6, then this is the truth. But even the 6 of us were able to show a better construction, a little bit better construction for larger k's. So we obtained a better construction by a ratio of 15/16. But then some more clever people came. So a year later, at least this is the time when the papers appeared. So Morrison, Noel, and Scott, they proved that as k tends to infinity, the exponent can be decreased from about k to something definitely smaller than k, so something like 0.98 times k. Okay, so probably this is one of the most interesting questions among these saturation problems, to find the coefficient of k in the exponent for the saturation number of the k chain. Okay, so what else was done before? So there is a paper by 7 people, so even more than the 6 authors paper that we had. So the authors are Ferrara, Kay, Kramer, Martin, Reininger, Smith, and Sullivan. And what they did is that they considered only the induced saturation problem for specific posets and some nice classes of posets, and they found that as opposed to the K chain, they tend to infinity as the ground set is increased. And they also, so this was the major part of their work, but for all the posets they considered, they always noted that the non-induced saturation version is trivially somehow there's a constant bound that is independent of the size of the ground set. Okay, then last year there was a manuscript uploaded to arXiv by Martin, Smith, and Walker. They improved some of the lower bounds that were obtained here. And then just a couple of days before our manuscript went online on arXiv, a Romanian PhD student from Cambridge, Ivan, she showed even better lower bounds for 2 particular posets. Again, for the induced saturation function, so one poset is the butterfly poset. I will talk about it later, and the other one is the ant poset. Okay, so this is, at least as far as I'm concerned, these are all the known results on saturation forbidden subposet problems. But if you are aware of others, then please send it to me. Okay, so what are our results? So the main result I will show you some non-induced, or at least one non-induced result, and 1 or 2 induced results. Okay, so about the non-induced result. So basically it says that the people from the previous slide, they were absolutely right not to consider non-induced versions, because they are always, I mean, this is always bounded by a constant. So the saturation function, the non-induced saturation function, no matter what the poset P is, it's always bounded by a function of the size of the poset. So but this is all what it depends on. So it's independent of the size of the ground set. And okay. So my first remark is that this is relatively sharp. So if we replace this part here by a k, meaning that we are now looking at posets of size on k elements, then the exponential upper bound cannot be improved by much, because the lower bound that we had for the chain of size k. So what is for sure that that in worst case, the saturation function can be exponential, and it cannot be larger because of this new theorem of ours. Okay, and what we conjectured based on this result of ours and based on this lower bound from several years ago, that probably among all k-element posets, the hardest to saturate is the chain. So this is a conjecture that we think to be true. We have no idea how to prove that, but anyway. Okay, so actually I will show you the proof of this theorem. So let's start. So the way how it goes, we will use what we call the greedy collects algorithm. And even if you understand all 3 words, which I assume most of you do, then it's not going to be exactly what you would expect. So what's a greedy algorithm? For a greedy algorithm, in the order the sets of the subsets of the underlying set. So if the underlying set has size n, then there are 2 to the n of them. So we have some order f, and for the subsets f1, f2, and so on up to f to the f sub 2 to the n. And we set our family at the beginning to be empty, and then we treat the subsets one by one. We want to add them unless, of course, they create a copy of P, because what we are aiming at is to create a P-saturating family, meaning that it shouldn't contain any copy of P, but with adding a new subset, there should be always created a copy of P. So what we do in this greedy algorithm, whenever we consider the I plus first set, then we look at whether together with the already obtained family, whether it's still P-free. If it is, then we add this new set. If it's not, so there is a copy of P, then we don't add it and we move on to the next set. So at the very end, when we do this for all the 2 to the n many subsets, at the very end, of course, we get a P-saturating family. Why is that so? Because, well, we were cautious enough to avoid all copies of P, because if there was a copy, then, of course, it consists of several subsets, and the one that was added last, it shouldn't have been added. So that's why it is P-free, and it's P-saturating because all the subsets that were not added, they were not added for a reason, because together with some subsets in the family, they would create a P. So that's why this is P-saturating. Okay, so this holds for any kind of greedy algorithm, and of course the important part is this sum. So I have 2 to the n factorial many possible orders to choose from, and of course I will take the Collex order or something related to that. So what is the Collex ordering? Well, it's about, we can order finite subsets of the positive integers in the following way. For two sets, A and B, we look at the symmetric difference of the two sets, and we look at the maximal element, the largest element of this symmetric difference. And if it belongs to B, then B is the larger. If it belongs to A, then A is the larger. So let's have an example. So if A is 1, 3, 5, 7, 9, and B is 2, 5, 8, 9, then the symmetric difference is 1, 3, 7, and 2 and 8. Out of these numbers, 8 is the largest. So among these two sets, B is the larger in the colexicographic ordering. So how does the colexicographic ordering look like? So the smallest set, or the smallest element of this ordering, is the empty set, then singleton 1, singleton 2, 1, 2, singleton 3, 1, 3, 2, 3, and so on. So this is how the colexicographic ordering looks like. And as I already warned you, this is not the ordering that we will consider, but instead, we will do the following. We will consider the Collex ordering, but only on the first half of the set. So that means we take those sets, they will be denoted by Fs, that do not contain the largest element n of the ground set. And then we order them according to this colexicographic order. And for any I between 1 and 2 to the n minus 1, Gi is just the complement. So G1 is the complement of F1, G2 is the complement of F2. So basically there we just reverse the order. And then the order that we are going to consider looks like this. I take the very first element of the Collex order and then its complement. Then the second element of the Collex order and then the complement. And the third element of the Collex order and then the complement, and so on. So in particular, we'll have 2 to the n minus 1 many pairs, and they are ordered according to their F set in the Collex ordering, and the G's, they are just the complements, and they are considered immediately after their counterparts. Okay, so this is how it's going to work. Okay, so let's see how, what's the order for the subset. So we start with the empty set, then its complement, so the whole underlying set. Then we take singleton 1 and its complement, singleton 2 and its complement, the pair 1, 2 and its complement, and the last pair to consider is the interval from 1 to n minus 1, and its complement, which is just the singleton n. So this is the last set, last subset of our ground set that we consider in this algorithm. Okay. So this is just a formal repetition of this. The only difference here that instead of indexing the families one by one for every subset, I here indexed it by pairs, meaning that instead of having 2 to the n many steps in the algorithm, we have just half of that, 2 to the n minus 1, because we have one family for each pair. Okay. So our claim is that no matter what P is, so remember, so the greedy collects process says that do this greedy thing with this order, meaning that the first set is the empty set, then its complement, then the singleton one, then its complement, and so on. And if we do it for a poset P on K element, so that means that we add the set if it doesn't create a non-induced copy of P, and if it does, then we don't add it. And if this poset P contains K elements, then actually we could stop our process after pair number 2 to the K minus 3. So all the remaining ones, no matter what n is, so no matter how large n is, most of the pairs will be untouched. So after the pair 2 to the K minus 3, nothing will be added. And then, of course, because in every pair there are two sets, so it's 2 times 2 to the K minus 3, so we will have this bound 2 to the K minus 2, which was promised at the theorem. Okay, so think about it. What are the first 2 to the K minus 3 pairs? Well, actually, it's just the construction that I showed you to be chain saturating, chain of length K. So this is exactly the construction that we had for in the 2013 paper with Donny Gardner and others. So it says that somehow this is a, well, I wouldn't say a universal construction, but anyway, this is a construction which is saturating for the chain, and which contains a saturating family for any other K element poset P. Okay, so how will the proof go? So here's a hint. So suppose that we are doing the greedy collects process, and at some moment we are considering this one element set, L plus 1, say. That's the only element of the set. And suppose that the greedy collects process doesn't add this set to the family, because it creates a copy of P, whatever P is, together, of course, with those sets that were already added to our family. So can we say something about other sets just based on the fact that this singleton is not added? For example, can we say something about the next singleton, or can we say something about this pair that comes after L plus 1? So this is, well, what I wrote here is L plus 5 and L plus 17. So this black pair is for this set, and this purple point is for this singleton set. Well, I claim that if this one was not added, then neither will be added these two sets. So why is that so? Because let's look at all those sets that were considered so far in the greedy collects process. Well, this is a set, a singleton, that doesn't contain the largest element. So this is an F. So what are the sets that were considered so far? Well, those sets that precedes this singleton in the collects order. And what are those? Well, they are the subsets of the first L elements of the ground set. So these are denoted by blue. So they all live in here. And of course, they're complements. So and how do the complements look like? Well, we have something here, and we have all the elements from here. And what we need to observe, that with respect to these, the green dot and the purple dot, or the pair of the black dots, they behave just the same. They are not in containment relation with any of these, and they are all contained, this one, and this one, by all of these red guys. So it doesn't make a difference whether I want to add this one or this pair. If this one creates a copy of the forbidden poset P, then so will the other two. So if this is not added, then I won't be able to add these two either. Okay, So this is the observation, and the next lemma, maybe I will skip the proof, but the next lemma says something in the counter positive, meaning that, so here what I said, that if this is not added, then these two sets are not going to be added either. So now I will say that if something is added, then something else before was added too. And so as I said, I skipped the proof, but I will show you the four statements, small statements of the lemma. So what kind of things are there? Okay, so maybe okay, so this is important. So m sub I denotes the largest element of the set f sub I. So the first statement of the lemma, so if I have a set in my family, born in the greedy collects order or greedy collects process, it was added, and this is its maximum element. Then if I remove this maximum element and I obtain this other set, that was also added before. This is the first statement. And then the second statement says that, again, I have an F, meaning this set doesn't contain the largest element. Again, the red dot signals the largest element of this set. And then if I add all the elements coming after, so this interval here, then again, it was picked before. Statement number 3 is now, the last two statements are about G's. That means sets that do contain the last element, n. So how do we get, of course, how do we realize that which element is m sub I? Well, m sub I is the largest element of f sub I, and g sub I is the complement. So this blue set is now the complement of f sub I. So that means that m sub I is the largest element that is missing from here. So statement number 3 says that if I have such a set that is added at some point of the greedy collects process, then if I put there the largest element missing, then this was already added in the family. And the last statement is that, okay, again, we start with the set G sub I, so it contains the largest element, and I consider, or I remove this last interval, so whatever we have before not having an element here, and if I remove this part, then again, this set was added before, at the previous step of the process, this set was added. If this was added, then this was added too. Okay, so how to finish the proof of the theorem using these four statements? So what do we need to prove? We need to prove that nothing after the 2 to the k minus third pair will be added. So suppose there is something that is added. So I have, again, two options. Either H is an F or H is a G, meaning that either H contains the largest element N, or and then it's a G, or it doesn't contain and then it's an F. So I will only show you the first case when H is a subset supposedly added after the first 2 to the k minus 3 many pairs, and still it doesn't contain the element n. So then what? Well, so this is f sub I. Its elements are h1, h2, and so on, hl. So this is the largest one. So this is m sub I with the notation of the previous slides. And what do we know about m sub I? We know that, sorry about this. So we know that this is at least, or it's strictly larger than k minus 3. Why is it so? Because of this condition that we know that the first 2 to the k minus 3 many pairs, they have all the subsets of the first k minus 3 elements. So if we have a pair coming later and we consider its F version, then its largest element is strictly larger than k minus 3, and it is strictly smaller than n because it's an F set, so it doesn't contain n. Okay, then what do? Then we apply statement number 1 of the lemma. We apply it multiple times, actually L times. So we first remove the largest element, then we remove the second largest element, and so on. And based on the statement of the lemma, they are all in our family. So that means we obtained a chain of length L plus 1 already. Okay, so far so good. Then what? Then we want to apply statement number 2, which says that, okay, this blue part is the set that that was supposed to be added. Then we know that this is an F, so that means I can add whatever comes after its largest element. So I do, and this newly obtained set, it is also in the family. Okay, and then what? And then starting from this set, I can apply statement number 3 and add the missing elements one by one, starting from the largest one, second largest one, and so on, up till I fill in all the elements and I get the whole underlying set. And a little bit of thinking gives me that the number of sets here is m sub I, so this is this element, minus L, so the number of green dots here, plus 1, because I go from 0 to m sub I minus L. So this is a chain, and I can put together these two chains, L plus, chain of length L plus 1, chain of length this much, and altogether, what I get is a chain of length m sub I plus 2. But m sub I is strictly larger than k minus 3, so that means m sub I plus 2 is at least k. So that means that if I added such a set after the first 2 to the k minus 3 many pairs, then actually the family of the greedy collects process contains a chain of length k. Now, so far, everything I said is valid both for the non-induced and the induced case. And now comes my last sentence about this proof, is that I have a contradiction, but only in the non-induced case. Why is that so? Because any k element poset P is a subposet, a non-induced subposet of the chain of length k. Of course, it's not true for the induced version. There we have nothing and there is no contradiction. But in this way, so because we have now, so our contradictory assumption was that we indeed added something after this 2 to the k minus third first pairs. And then we obtained the contradiction that, okay, but then we have a k chain, which is impossible because every k chain contains actually any poset P on k elements. And we know that the greedy collects process doesn't create any copy of P, so now we have a contradiction. Well, of course, if you believe me that the other case when the added set H is not an F but a G, but it's very similar, so I hope you believe me. Okay, so this is the proof of the non-induced results. We have several other results in the paper. So for non-induced results for specific posets where the bound is not just a general bound, but either we have the precise saturation number or something very close to it. But now let me move on to the induced results that we obtain. So as I said, the greedy collects algorithm can be defined for the induced case. The proof, what I told you, it doesn't work. We know that it doesn't work because, I mean, the result would have given us that the saturation function is bounded by a constant independent of n, of the size of the ground set, and we know it from earlier results of many people that there are posets for which the induced saturation function tends to infinity with n, with the size of the ground set. So we can't expect that. But still, we can look at how the greedy collects algorithm works in the induced case. Well, actually, it's not that good. I will show you. And we could be interested that what can this process do when we know that the saturation function tends to infinity. But before that, let me show you a lemma which is actually implicit in the work of Ferrara and others. So it gives us a kind of a characterization that when is the induced saturation function is bounded by a constant that is independent of n. So these two things are equivalent. First, that the induced saturation function is bounded by a constant independently of the size of the underlying set, and the fact that one is able to find a p-saturating family such that on a ground set of size m and two elements x and y in the ground set such that they are not separated by this saturating family. What does it mean being separated? Well, this blue rectangle, it separates x and y because it contains x and doesn't contain y. So separation means that a set separates two elements if it contains one of them but not the other. So not separating means that it doesn't separate these two particular elements, meaning that every set in the family either contains both of them or none of them. Okay, so the proof actually is quite simple. First, there are two directions because this is an equivalent statement. So two follows from one simply by the fact that we know that to separate all pairs of elements of a ground set of size m, we need at least log m many sets. So if we um, do if we have only a family of a constant size, then for large enough m, it won't be able to separate because this log m will surpass this constant. Okay, the other direction is it's just an observation. So, well, if f does not separate x and y, then f consists, the family consists of two parts. But those sets that don't contain neither x nor y, and those sets that contain both of them. And so, well, this family, we have it only for a ground set of size m, but based on this family, we can extend it to arbitrary larger ground sets in this way. So I keep those sets that do not contain x and y, and to these sets, I add the new elements. So if I, instead of a ground set of size m, I have now a larger ground set n, then all the new elements will be added to all of these sets, and it's not hard to verify that the family that I obtained in this way is p-saturating again. Okay, so anyway, so this is the statement. The statement is that the induced saturation number is bounded by a constant if and only if there is a p-saturating family that is not separating. Now, what are the consequences of this lemma? Well, first of all, first consequence is that there is a dichotomy phenomenon, meaning that the induced saturation function is either at most a constant or it is at least log of n. So you cannot, no matter what is your favorite poset p, it cannot happen that the order of magnitude of the induced saturation function is, say, log n or inverse Ackermann or anything like that. It always should be at least log of n. And actually what we conjecture that is far from truth, we conjecture that either the induced saturation function is a constant or it's at least linear. Second consequence is that to decide that whether the induced saturation number of a poset is bounded by a constant that doesn't depend on the ground set size. Well, this problem is recursively enumerable because all what we do is just greedily, well, for every n, we check that we check all families, whether they are saturating, and if they are saturating, then we also check whether they do not separate a particular pair. And if we find that, then that is a proof based on the lemma that the induced saturation number is bounded. So we have a proof for boundedness, but we don't have a proof for being unbounded. So it's a question that whether this problem is recursive, whether there is an algorithm that decides for any poset p whether the saturation number is bounded by a constant or it grows with the size of the underlying set. Okay, consequence number 3. So now back to the greedy collects process. What one can do, okay, take your favorite poset P and a size for the ground set, hopefully not very large, or if you have a very strong computer or quick computer, then it can be even larger. And then look whether the last two elements, n minus 1 and n, are not separated, or whether they are separated or not. And if they are not, that's good news based on the lemma, because then we know that this is bounded. Of course, I mean, the induced saturation function is bounded. Of course, there is no guarantee that just because the greedy collex doesn't find the appropriate family to prove that it's bounded, it doesn't mean that that it's unbounded. But this is what we have. So I'm okay. So yeah, if it if it does separate, then nothing follows. And yet, when the greedy collex algorithm can be useful, even in cases when the induced saturation function tends to infinity. And let me show you this. Well, showing me it's quite an exaggeration. I will just hint what's going on. So the butterfly poset, it has 4 elements, A, B, C, and D. So A, B, they are the 2 small elements, and C and D, they are the 2 upper elements. So C and D, they are both larger than A and B, and no other relation in there. And so what do we do? Well, we run the greedy collex for P, and we get a long list of sets, and they do separate n minus 1 and n, so there is no chance that it's going to be bounded, not to mention the fact that there are lower bounds, so we know that it won't separate this n minus 1 and n. And then I know that this is hard to take, or I mean, so anyway, so after looking at the listed sets for a while, one can get actually the structure of what's going on, or what the output, what the structure of the output family is. Basically, it looks like, or almost like, 6 maximal chains. So the size of the output is always going to be 6n minus 10. And what one can do is, well, once we have a hint by the computer, and therefore a conjecture for what the collex greedy process gives, then we can prove it mathematically, or via induction, of course, that this is indeed the output of the greedy collex process. And then we immediately obtain an upper bound of 6n minus 10 for this butterfly poset. And luckily, just a couple of days before our manuscript went onto archive, this talented PhD student from Cambridge showed a linear lower bound. So now we have the theorem that the induced saturation function of this particular poset is linear in terms of the size of the ground set. Okay, so if this went so well, then of course one can ask whether this greedy collex process always gives the correct order of magnitude. And the answer is no. We have counterexamples, unfortunately. So 2 times C3, this is, well, C3 is the chain of length 3. So 2C3 is just a pair of chains of length 3 that are incomparable to each other. So the chain relations are the only relations that are there. And for that, seemingly the greedy collex process gives a quadratic family, but we had a linear upper bound. And even worse, we had, I won't define this diamond-like poset, but we have an example for which the greedy collex process gives a family that has an exponential size with respect to the size of the ground set. And actually, it wasn't very hard to find a linear family, a linear upper bound. But still, we do not have a counterexample for separating constant and non-constant. So it is still possible that the greedy collex process is good just to decide whether this induced saturation number is a constant or not. Of course, I wouldn't bet on this, but I just say that we don't have a counterexample for that. Okay, I'm getting closer to the end, but I want to show you one more result or conjecture, and just to show you that how little do we know about the induced saturation number. So there were already satisfying conditions for the saturation function not to be bounded. We extended, so we added some more, and we also had satisfying conditions for having the saturation number bounded, but we still do not understand what is going on. And here is the simplest thing that, at least personally, I don't really understand why is this like that. So this is a poset on 2k elements. They are just k pairs. So this one is smaller than this one. This element is smaller than this element, and so on. So if you wish, then this poset is the one of which the Hasse diagram is a matching of size k. And we conjecture, because this is what we obtained from computers or whatever, that that the fact that whether the induced saturation function of this poset is bounded by a constant independently of the ground set size or not, that depends on the parity of k. How many edges do we have in the matching? So if k is odd, then it is bounded according to our conjecture. If it's even, then it's unbounded. At least this is what we conjecture. So what do we have? For odd, so for positive results in the sense that then it's bounded, well, for k equals 1, you just take the empty set, or you take the whole ground set, and that would give you a saturating family. But for k equals 3 and 5, we had some nice constructions, and then we were very happy and saw that it would work for larger values of k. So I mean, the construction was about, or it involved circular intervals. So we, instead of looking at the elements 1 to n as an interval, we just close the interval and get the circle. So n was a neighbor of 1 and so on. And then we have the circular intervals, consecutive integers. And using these, we managed to come up with a non-separating family, and we conjectured that this is going to be saturated. If we pick every parameter appropriately, then this is going to be saturating for this KC2 poset. And as I said, it did work for k equals 3 and 5, but it didn't work for k equals 7. And at that moment, we saw that, okay, then probably k equals 1, 3, and 5 were outliers, and then from then on, everything will be unbounded. But then we had the greedy collects process, and it worked for 7. So now we conjecture that it should be like that for every odd value of k. But I mean, just because of that. So what do we know about the even case? Well, it's even worse, the even case, because all we have is that we can prove that for k equals 2, it is indeed unbounded. So actually, this is the theorem that we have, that if we have a 2C2 saturating family, then it must contain a maximal chain in the ground set. So therefore, it should have at least n+1 sets. The upper bound 2n is just if you take a maximal chain and add all the singletons, that's 2n many sets, and you can check by hand that this is 2C2 saturating. So I will show you hopefully in like 5 minutes, how this proof goes. Okay. So what we want to do is that we introduce the downset of G with respect to the family F. So these are, I mean, this is another family of sets. All the sets in the family F that are strict subsets of G. So why is it meaningful? Because just not even saturating, just the fact that a family is 2C2 free, that it doesn't contain an induced copy of two comparable pairs, that can be described using these downsets. Why? So we claim that if we have an induced 2C2 free family, then if we take f and f prime in the family and look at their downsets, then either one contains the other or the other contains the first one, or, well, they can be, of course, the same, and then both contain the other. Why is that so? Because if not, then if the downset of f prime doesn't contain the downset of f, then there is a d which is below f, but not below f prime. And if the downset of f doesn't contain the downset of f prime, then there is a d prime, which is just below f prime, but not below f. And then these four sets, they indeed form an induced copy of two pairs in containment. So this is one pair, this is the other. Okay. So based on that, if we have a family F, which is 2C2 free, then using the downsets, we can order them, namely in such a way that they form a nested sequence. So the first one has the largest downset, then the second one the next largest, and so on. So they are nested. Of course, repetitions are allowed, so it can happen that the downsets are the same. But definitely there is a nestedness here. And of course, we can assume that the whole ground set and the empty set is added because they are comparable to all the subsets of the ground set. So they wouldn't help to form an induced copy of 2C2 because in 2C2 we need 4 elements. For each of them, there are at least 2 other which is not comparable to that. And well, for the whole ground set, it is, and for the empty set, it is impossible. So therefore, we have to add. If you want to saturate, then we have to add them. Okay. So then we ordered the elements of the family F in this way, and then we define the G's. So G sub j is the intersection of the first j sets of the family in the previously determined order. So, well, here a red dot is missing. Then for the second one, it's still the same. And for the third one, so this one is supposed to be the intersection of this set, and this set. And this is, of course, well, in my ugly drawing, this is the Hasse diagram of the Boolean lattice. This is the complete of the ground set, and this here is the empty set. And then this guy is the intersection of this, and this one is the intersection of this, and this, and finally we get there. And so the claim will be that, okay, now we defined the red ones, the red sets, the G's, and the claim is that, well, they form a set. I mean, they form a chain, not necessarily a maximal chain, but because we intersected more and more sets, then of course we have smaller and smaller sets. And the claim is that whatever is in between 2 consecutive elements, then they should belong. If F is 2C2 saturating, then these sets should belong to the family. This is what I'm going to prove. And okay, so here we need a lemma. So remember, the F's are the original sets in the family, and the G's are the intersections. And the claim is that, okay, of course, the G's, the intersections might be much smaller than the original sets, but the downsets, they are relatively the same. So the only thing that could happen that GH loses from its downset, well, itself, because GH, it contains itself, but not strictly, so therefore it's not there. So this is the statement of the claim. Well, the first part, this part is easy because GH is just the intersection of all the first H F sets. So in particular, it is a subset of F sub H. So clearly the downset of a larger set contains the downset of the smaller set. So there is basically nothing to prove here. On the other hand, so for this other containment, we have now we use the fact that this is a 2C2 free family. So therefore, we had this nestedness. So the way how we enumerated the sets of the family, we have that the downsets are nested. So for every I which is smaller than H, the downset of F sub I contains the downset of F sub H. So therefore, the downset of F sub H is actually the intersection of the downsets of the first H downset. And therefore, because what is GH? Well, GH is just the intersection of all the FIs. So whatever is, so this means that here we have all the sets that are below all the FIs. Well, if something is below all the FIs, then it's below all the GH. I mean, it's below GH. Well, below means that it can be actually equal. So the only thing that is missing from here is GH itself. So this this finishes the proof of this claim. Okay, and now, so remember, this is what I want to show, that we define this this chain, and I want to show that whatever is in between two consecutive elements of the chain, that it should also belong to F. And if that is so, then we indeed get that the the family F contains a maximal chain, and therefore its size is at least n+1. Okay, so this is, I think, the last slide of the talk. So I need to show, as I said, that if I have a set X, which is a subset of G sub J, maybe it is indeed G sub J, and it is a strict superset of G sub J+1, then it should belong to F. So towards a contradiction, suppose it doesn't belong. Then, if it doesn't belong, now I use the fact, this for the first time, I think, that that F is 2C2 saturating. So if I add X to this family, then an induced copy of this poset should be born. So that means, well, X must be part of that induced copy. So that means the other pair is incomparable to X. So the other pair, A and B, they should come from the family F. Okay, well, A and B from the family F, that means that they are some Fk and some Fl, and because A is a subset of B, therefore B is listed first, so its index is smaller than the index of A. And now we have two cases, and this time I will show you both cases because they fit on this slide. So the first case is when the index of BL is at most J, so at most this J that we are talking about. So then what do we have? Well, X is a subset of G sub J. Well, what's the definition of G sub J? It's the intersection of all the previous FIs. In particular, FL is one of them, and FL is B, meaning that B contains X, which is a contradiction because X and B are not supposed to be in containment relation. So for this case, I got my contradiction. And for the other case, when L is at least J+1, then I will apply the claim. And I will get a contradiction with the fact that A and X are supposed to be incomparable. So what is A? Well, A is a subset of B, and B has a spy name F sub L. So in particular, A is a member of the downset of F sub L. And because the Fs are nested, I mean, the downsets of the Fs are nested, and we are in the case L is at least J+1, we have this containment. Now I use the claim. According to the claim, the downset of F sub J+1 is contained in the downset of G sub J+1 plus G sub J+1 itself. But whatever is below G sub J+1, it's of course below X. And even G sub J+1 is also below X. So that means that A is below X. So indeed, A is a subset of X, which is a contradiction because they are not supposed to be comparable. So I obtained a contradiction in both cases, so the proof is done. It's finished. So that's all I wanted to show you. And as a reminder from Demeter, there is a nice table in our manuscript that we uploaded to archive, which contains all the results that either we or the other manuscripts obtained. So if you are interested in specific values of the saturation function, I mean the value of the saturation function for specific posets or classes of posets, then you can take a look there. And thank you for your attention. I would like to stop now. I don't know how we do this. So if anyone has a question, then probably there is a way, which I don't know how is it, that he or she can ask this question. So I will wait for.
Questions?
Yeah, are there, oh. So many of the microphones are now on, so anyone who has a question, then I'm happy to trying to answer that.
Is the 2 to the p ever sharp in the non-induced case?
As I said, for the that's for sure that for the with the greedy Collatz algorithm, we cannot do any better because for the chain it gives exactly that much. And also, if you want to be more clever and not use something else, then what we know is that exponential is needed because we have a lower bound for the chain, which is 2 to the roughly k over 2. K minus 3 over 2. So it's going to be exponential, whether it's, and well, the coefficient of k in the exponent, we don't know. So it's somewhere between 1/2 and 1, but we don't know the exact value there.
But we conjecture that it's not sharp, that the chain gives the upper bound, and for that we have something better, right? 0.98.
Yeah, exactly. So if I go back, I don't know if I can do that, but let me just go back. From here. Oops. Yeah, so Morrison, Noel, and Scott, they showed this result for the chain. Oops. So there is an improvement. Instead of 2 to the k, they have 2 to the 0.998 times k. And we have a conjecture, as Demeter mentioned, this conjecture that the k chain is
we cannot see the slides, at least I can't.
I'm sorry, then what did I do? Probably, but okay. So now, can you now see the slides?
Yeah.
Okay. So this is the conjecture. The conjecture is that if you consider non-induced saturation, then what we conjecture is that the chain is the hardest to saturate. And if this conjecture is true, as Demeter mentioned, then because of this result of Morrison, Noel, and Scott, then the coefficient shouldn't be 1, but something smaller, because we know that for the chain, something smaller is true, but we don't know whether our conjecture holds, that whether it's indeed the chain which is hardest to saturate. Okay.
Okay, thanks.
Okay. Any other questions?
Ha nincs, akkor köszönjük szépen az előadást.
Én is köszönöm. Akkor most kikapcsolom. Nika, could you stop the meeting, because it seems there are no more questions. Thank you.